Okay, I welcome you back to my video lecture presentation. Myself, C. Ashok Kumar, Professor, Department of EEE. And my course name is Electronic Device and Circuit. And my topic name is the half-wave rectifier, operation as well as the derivation of parameters. And the overview of my presentation goes on like this. First, I will be saying about the operation, circuit diagram and operation of half-wave rectifier. And then I will be deriving the parameters of the half-wave rectifier which judges the performance. Okay, one by one I will be deriving, and finally I will be recapping the things whatever I discuss. Okay, first topic, that is a half-wave rectifier. So in the last class I said about the types of rectifiers. One is the half-wave rectifier, second one is the full-wave rectifier, conventional type, and third one is a bridge rectifier. So first type is the half-wave rectifier. As you can see, this is a circuit diagram. Okay, circuit diagram, and this is the input where you will be providing to a conventional transformer primary. Okay, so this is the AC input. Okay, that is called as a VI. And then here, as you can see here, I am making use of only a single diode. In my discussion about the operation, I will be assuming the diode to be as an ideal one. Ideal one means whenever it is forward bias, it offers zero resistance and the current flown will be maximum. Whenever it is in the reverse bias, the current will be minimum, zero, and the resistance offered by the diode will be infinity. Okay, so I am assuming the diode to be an ideal one in my operation. Okay, this is a diode, and here as you can see, this is a load resistance across which I need to measure the output voltage. So here I am providing the input voltage, which is an AC signal, AC voltage, and here I am taking out the output voltage across this load resistance RL. Okay, so this is the circuit diagram of a half-wave rectifier. Okay, so now let us go to the operation here. So because it is AC input is represented like this. As you can see, VI, a sinusoidal signal. Okay, so this is a positive half cycle and this is a negative half cycle. Because it is AC signal, I am representing like this. And here, as you can see here, the angle omega t, angle of conduction, whenever the VI is in between 0 to pi, this is a positive half cycle. Whenever omega t is in between pi to 2 pi, it is a negative half cycle. And here, as you can see here, this maximum value is represented by Vm. Okay, and here also maximum value defined in a negative manner, minus Vm. Okay, so here I am providing this input voltage for my half-wave rectifier circuit. Okay, here I am providing the input voltage. Okay, so let us segregate the operation into two parts. Part 1, whenever omega t is in between 0 to pi, and whenever omega t is in between pi to 2 pi, what happens to the diode? Okay. Okay, whenever omega t is in between 0 to pi, okay, so this terminal will become positive and this will become negative. Okay, so the diode, as you can see, this is the anode and this is the cathode of the diode. Anode is more positive, that's why the diode will be forward bias. Whenever a diode is forward bias, the current will be flown through the diode in this manner through the load resistance RL. Okay, let it be I of t. I am representing the current as I of t. Why? Because the diode is forward bias, the current must be flown through the diode, and that current will be flown through the load resistance RL, producing a voltage drop across the load resistance RL. I am calling it as a V0. V0 is the output voltage. Okay, for the provided input voltage, I am getting output voltage. Okay, Vi is the input. Whenever omega t is in between 0 to pi, I am getting a output voltage of Vm. Peak value is Vm. Okay, this is about the operation whenever omega t is in between 0 to pi. Okay, whenever during the negative half cycle means omega t is in between pi to 2 pi. So what happens here? This particular terminal will be negative with respect to this particular terminal. So what happens to the diode here? The anode and this is a cathode. Anode is negative and cathode, and compared with cathode more negative and compared with cathode. That's why this diode will be reverse bias. Whenever diode is reverse bias, it acts like a open circuit, okay, and the current flown will be equal to 0. No current will be flown through the diode. Why? Because it is reverse bias. So that's why here there is no chance of any current to flow through the load resistance RL. So that's why here the voltage drop across this load resistance RL is equal to 0 into RL. Okay, 0 into RL, that is nothing but V0 is equal to 0. That's why you can observe here from pi to 2 pi, output voltage is 0. From 0 to pi, when omega t is in between 0 to pi, the output voltage defined is same as the input voltage Vm. And whenever omega t is in between pi to 2 pi during the negative half cycle, because the diode is reverse bias, no current will be flown. That's why the output voltage defined will be equal to 0. So that's why here, as you can see, here output will be equal to 0. So I can write an equation of output voltage depending upon the angle of conduction whenever omega t is in between 0 to pi, that means here. So what is the value of V0 here? V0 is equal to Vm sine omega t. I am writing about this equation, output voltage equation, okay. Whenever omega t is in between 0 to pi, V0 is equal to Vm sine omega t. Okay, otherwise what happens? Whenever omega t is in between pi to 2 pi, what is happening here? Output voltage V0 will be equal to 0. Okay, this is the equation of output voltage across load resistance RL. Okay, V0 is equal to Vm sine omega t whenever omega t is in between 0 to pi, and V0 is equal to 0 whenever omega t is in between pi to 2 pi. So these are about the operation. Next, let us derive the parameters related with the rectifier. So many parameters are there. Let me say about those parameters. First, I need to obtain the value of the efficiency, rectifier efficiency. That will be discussed one by one afterwards. Rectifier efficiency. Second, I need to calculate the ripple factor. This is a main important parameter that judges the performance of the rectifier, any rectifier, ripple factor. And next one is about the TUF, transformer utilization factor. How far the rectifier is utilizing the transformer, okay, for the conversion of AC to DC, okay. Next, so many parameters are there, one by one. Let us see here. Rectifier efficiency, ripple factor, TUF, and ripple voltage, like that, form factor, peak factor, like that. So many parameters are there. So in order to derive this, calculate these parameters, we need to derive basically two parameters we need to derive. One is called as the average voltage across the load. Second one is the RMS voltage across the load. Okay, that first we need to derive. So for that, you need to know about the formulas related with the calculation of the first one is, as you can see here, first I need to calculate the average or DC content of voltage across the load. Okay, as you can see here, load is RL. I need to calculate this output voltage, which is a DC voltage. Okay, that's why I am calling it as a V average, average or DC content. So the formula for that one is V DC is equal to 1 by 2 pi, okay, integral 0 to 2 pi, 0 to 2 pi. So V naught of d of omega t. So this is a formula, general formula. So here I am segregating this integration into two parts, integral 0 to pi plus integral pi to 2 pi. Okay, integral 0 to pi v naught of t d of omega t plus integral pi to 2 pi v naught of t d of omega t. As you already know, v naught of t is equal to Vm sin omega t whenever the omega t is in between 0 to pi. Otherwise, it will be equal to 0. So that's why here directly the equation is written like this: Va average or VDC is equal to 1 by 2 pi integral 0 to pi. So what is the value of V naught of t? That is Vm sin omega t. Okay, into d of omega t. And what is the value of V naught of t whenever omega t is in between pi to 2 pi? The diode is reverse bias and the current will be equal to 0. That's why V naught of t is equal to 0. That's why here 0. So that's why here we can ignore the second term. Why? Because it is, the value is 0. Okay. So here Vm by pi, if you take this Vm outside because it is a constant, Vm by 2 pi. So integral sin omega t. Integral sin omega t is nothing but minus cos omega t. And if I apply the limits of integration, so you will be getting cos pi minus cos 0. So you will be getting totally you will be getting 2 and 2 cancel, you will be getting Vm by pi. Okay. So V average value or VDC value is equal to Vm by pi. Okay. So you know the voltage and you can obtain the value of the current IDC. So IDC is equal to VDC by RL. RL is a load resistor. So VDC, you know the value of VDC as Vm by pi. So Vm by pi into 1 by RL, you will be getting Im by pi. So here V average is equal to Vm by pi, I average is equal to Im by pi. So here this particular operation and derivation, we assume the diode to be an ideal one. Suppose if we consider the diode resistance into account, that is called as RF, forward resistance of the diode, as well as the transformer secondary winding resistance also into account, then what is the value of VDC? So you know the value of VDC as Vm by pi, ideal case. But here I am saying that I am considering RF as well as RS. So that's why here this particular equation can be changed as Vm by pi minus the drop across the diode forward resistance of the diode is given, as well as the secondary winding resistance also will be given. So that's why here Vm by pi minus of IDC into RS plus RF. Okay. So in the same manner, IDC can be calculated in terms of voltage. So VDC by RF plus RL. So we'll be getting Vm by pi into RS plus RF plus RL. Okay. So in the maximum cases, you will be ignoring the value of RS, you will be ignoring the value of RL. Okay. So finally, we can write IDC as Vm by pi into RL. Okay. So next, I calculated VDC or V average value. Now I need to calculate RMS value. RMS value of the voltage across the load, that is represented as VRMS. So root mean square. So I am writing the formula here, VRMS is equal to 1 by 2 pi. So here integral 0 to 2 pi. So here V naught of t square d of omega t. Okay. So here the formula will be going on like this: 1 by 2 pi integral 0 to 2 pi V naught square of t d of omega t. So here root is there, mean is there, s is there. Mean means 1 by 2 pi integral 0 to 2 pi V naught of t d of omega t. Root means, as you can see here, 1 by 2 is there, that is nothing but a root. And square means I am squaring the value of the output voltage. Okay, this is a basic formula. And already I said, whenever omega t is in between 0 to pi, the V naught of t is equal to Vm sin omega t, otherwise it will be equal to 0. So that's why here I am writing the formula like this: 1 by 2 pi integral 0 to pi. I am not taking the second integral part, that is pi to 2 pi. Why? Because the output voltage defined will be equal to 0. So that's why here 0 to pi Vm square sine square omega t d of omega t whole to the power of 1 by 2. Okay. So here it is square, that's why Vm square becomes Vm taken outside, and here 1 by 4. So here the sine square omega t can be written as sine square theta can be written as 1 minus cos 2 theta by 2. So same thing here written 1 minus cos 2 omega t by 2, and here already 2 is there, so it becomes 4 pi. 1 by 4 pi integral 0 to pi 1 minus cos 2 omega t d of omega t. So 1 into d, if you separate this particular equation into two parts, the first part will be integral 0 to pi 1 into d of omega t minus integral 0 to pi cos 2 omega t d of omega t. Okay, if you integrate cos means you will be getting sine. If you apply the limits, sin n pi always it will be equal to 0. Sin n pi will be equal to 0. Sin 2 pi will be equal to 0. Sin pi will be equal to 0. Sin n pi will be equal to 0. That's why the second integrated portion will be tending to 0. So that's why here only term left is the first term integral 0 to pi 1 into d of omega t, and you need to apply the limits, and you will be getting pi minus 0, and finally you will be getting this Vm by 2. So Vrms value will be equal to Vm by 2. In the same manner, Irms value will be equal to Im by 2. Okay. So you know the value of VDC, you know the value of Vrms. Okay. So you know the value of VDC and you know the value of Vrms. You know the value of IDC, you know the value of Irms. So first parameter, important parameter I am calculating here is the ripple factor. So ripple factor decides the amount of ripples that are contained in the rectified output of a rectifier. Okay. If you know the value of ripple factor, you can judge the performance of the rectifier. Whenever it is very, very high, we can say that the rectification is not good. It is a poor one. So that's why here it is an important parameter we need to calculate for each and every rectifier. So the formula goes on like this: root over Vrms by root over the formula I am writing here, Vrms by VDC whole square minus 1. This is the formula. So Vrms value is Vm by 2, as you can see here, Vm by 2. And VDC value, what is the value of VDC here? Vm by pi. So Vm by 2 by Vm by pi whole square as per this formula minus 1. So you will be getting Vm will be cancelled, and you will be getting pi root over pi by 2 whole square minus 1, and you will be getting the value of 1.21. So the ripple factor is equal to 1.21 for half wave rectifier. Okay, this is a parameter 1 we calculated. And next is second parameter is the efficiency. So the efficiency means it is known as a rectifier efficiency. As you know, the efficiency is nothing but the ratio of output to input. Okay. So here the rectifier efficiency formula is written as PDC by PAC. PDC means the DC output power, and PAC means AC input power. How much amount of input power you are providing, and how much amount of AC input power is converted into DC output power, that we need to calculate. That's why the formula eta is equal to PDC by PAC. DC output power, rectifier output is a DC, and input power provided is AC. That's why PDC by PAC. So PDC means output DC power. So here I am writing the power equation can be written as P is equal to V square by R or I square into R. So here he had written V square by R. So VDC square by R. R is nothing but a load resistance, and VDC, you know the value of VDC as Vm by pi. And PAC also same. P is equal to V square by R. Vrms square by RL will be cancelled, and you will be getting Vm will be cancelled, and you will be getting 4 by pi square. That will be equal to 0.406. And if you talk in terms of percentage into 100, you will be getting 40.6. Okay. So the maximum efficiency of half wave rectifier is 40.6. 0.6. Okay. And next is about the transformer utilization factor. So you are utilizing a conventional transformer, primary winding will be there, secondary winding will be there. How far that we are utilizing the transformer for our conversion from AC to DC. Okay, that is a parameter that is called as a TUF, transformer utilization factor. So the formula goes on like this: DC power delivered to load, same as above, PDC. And here the difference lies here. Here not PAC, here AC rating of transformer secondary. Okay, that's why here the formula is written like this: PDC by PAC rated. Okay, so PAC rated means in the half-wave rectifying circuit, the rated voltage of transformer secondary. As you know, here this is a transformer primary and this is a transformer secondary. Secondary winding rating will be provided by the manufacturers. Okay, that has to be taken granted. So that's why here the value will be taken as Vm by root 2. So that's why here, as you can see here, we need to calculate AC rated power. Okay, so that's why here for voltage I am writing the rated value of the transformer secondary Vm by root 2. Okay, whatever may be the rectifier, you need to take this particular parameter into account. You need to take it granted. And what about this RMS value of current? That depends upon the type of rectifier. So for our half-wave rectifier, what is the value of IRMS we got? What is the value of IRMS we got in our primary calculation? We got the IRMS value as Im by 2. As you can see here, if you go back, you can understand the things. So what is the IRMS value here? VRMS is equal to Vm by 2. IRMS means Im by 2. Okay. Only difference lies in the voltage or current. Whatever may be the type, whether it is voltage or current, same equation is valid. VRMS is equal to Vm by 2. IRMS is equal to Im by 2. So that's why here I am writing the AC IRMS value of current as Im by 2. Why? Because it is half-wave rectifier. So if you go for the calculation here, Im square by pi square, that is nothing but a PDC. PDC is Im by pi whole square, Im square by pi square into RL. And here Vm by root 2 into Im by 2. So you will be getting here Vm square by pi square into 1 by RL. And here Vm by root 2 is there. So here Im is there. I need to convert Im. I need to write the Im in terms of Vm. That's why here instead of Im, I am writing Im as Vm by RL. Okay. Im, I am writing Vm by RL. So here Vm square is there and here Vm into Vm square is there. And if you go for the calculation, RL will be cancelled and you will be getting 2 root 2 by pi square. That will be equal to 0.287. So the TUF of half-wave rectifier is 0.287. Okay. So that is about TUF calculation. And the next is an important parameter that is called as a peak inverse voltage. Okay, first let us define the peak inverse voltage. It is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. Okay, suppose here I am drawing, this is a half-wave rectifier. So here I am drawing the circuit diagram here. This is RL. So during the positive half cycle, a voltage V0 will be developed across the load resistance RL. Okay, why? Because the diode is forward bias. During the negative half cycle, what happens here? What happens? So this diode will be reverse bias. It acts like a open circuit. Okay, whatever the input voltage provided, it is an RMS value. I am representing its peak value Vm. But here it is open circuit and here RL is there. In the reverse bias, no current will be flown through the diode in order to flow through the load resistance RL. So that's why here whatever voltage that is there at the secondary input, that is nothing but Vm, that has to appear across this reverse bias diode. The maximum voltage that will be withstanded by this diode in the reverse mode must be Vm here. Okay, so that's why I can call this Vm as the peak inverse voltage of the diode in the half wave rectifier. Why? Because it has to withstand the provided input voltage in the reverse bias. So what is that value? Vm. Whenever the diode is forward bias, whatever the provided input voltage of the secondary will be appearing across the load resistance RL. Why? Because the load, this particular diode will be forward bias. It offers no resistance. So that's why here, whenever Vm, you are providing Vm here, that Vm will be appearing across the load resistance RL whenever diode is forward bias. Whenever the diode is reverse bias, it acts like a open circuit. I am providing Vm here. That Vm, why? Because current is not produced through that diode. So that's why here this Vm must appear across this reverse bias diode. That means it has to withstand an voltage of Vm across it in the reverse bias mode. So that is called as a peak inverse voltage. So it is a maximum reverse voltage that a diode can withstand. So what is the value here? The value will be equal to Vm. Okay. So for the half wave rectifier, the peak inverse voltage value will be equal to Vm. Okay. So the diode is reverse bias. Whatever the voltage that is provided here, that must be across the diode, not across the load resistance RL. Why? Because whenever the diode is forward bias, it won't offer any resistance. Whatever the voltage you are providing here, that will be appeared across the load resistance RL whenever diode is forward bias. Whenever diode is reverse bias, the provided voltage will appear, it has to appear across the diode in the reverse bias. It must not appear across RL. Why? Because the diode is reverse bias, no current will be flown through the diode in order to flow through the load resistance RL. So that's why PIV for half wave rectifier is Vm. So with this, I can stop here and let me recap the things here. First, I explained about the circuit diagram of half wave rectifier. Its operation I explained with the help of circuit diagram and waveforms. And next, I derived the parameters related with the rectifier which judges the performance of the rectifier. So one is called as the rectifier efficiency, which is represented as theta, and next one is the ripple factor, which is represented like this, and next is the TUF, transformer utilization ratio, and finally the peak inverse voltage, PIV. Okay, rectifier efficiency is PDC by PAC, and ripple factor is root over VRMS square by VDC whole square minus 1, and TUF is a transformer utilization factor, that is equal to PDC by PAC rated. Okay, so rectifier efficiency is PDC by PAC, but here the TUF is PDC by PAC rated. That depends upon the granted value of the transformer secondary rating Vm by root 2. And PIV is the maximum voltage that must withstand by the diode in the reverse bias mode. That is the peak inverse voltage. Okay, with this I will be stopping here and I will be concluding, and I will be continuing in the next class with the other new topic that is called as a full wave rectifier. Thank you.